Okay, welcome to the lab. We're going to talk about some stuff here. We get going. Get started here in just a sec.
Mr.
Yes, sir.
Quick question about lab. In the post lab was about electron configuration and the electron dots.
Yeah.
I haven't learned those yet, so are we just going to skip that part?
Yeah, we're going to talk about that right here when everybody gets in. We're actually going to postpone the lab for today. We're going to continue lecturing to kind of catch up a little bit, and we're going to move it till next week. So hopefully by then we'll be able to hit all those things. Yeah, so it has a lot of some stuff that it's actually in the end of the next chapter in this particular experiment. So I think that's what we're going to do. We're just going to hold off on the experiment today. We're going to continue lecturing and get into the next chapter as well. And then hopefully by Monday there, that will kind of get us a little bit back on pace in terms of the experiment, because it does have a lot of stuff that is sort of towards the end of the next chapter and stuff like that. So every year they move that experiment around to different locations and times, and it kind of covers a couple of different chapters. So depending on sort of where it is, we're probably not there yet, obviously. So that's the game plan here for today. So what we're going to do is we're going to continue on here with chapter 4. We're going to get into chapter 11, as was the question there. It essentially has some stuff from this chapter we're currently talking about. It also has some stuff towards for the end of the next chapter and stuff like that. So the goal here is what we're going to do. We're going to finish up obviously chapter 4 here. Chapter 4 will be the last chapter that will be on the exam. The exam is going to be moved, as I think I mentioned last time as well. It's going to be moved to Wednesday. So we're going to do the exam on Wednesday. We're going to then I think we're going to move this experiment to Monday, seeing where we're at in terms of material. But tentatively, this experiment, this for today, which was experiment 8, I think, will be done on Monday. Exam will be Wednesday during lab time is when we're going to take that. So we'll have the exam during lab time. You'll take it through proctoral, and it'll be sort of a Canvas exam probably. I think at this point, I haven't written it yet, so I'm not sure. But it'll be some type of exam, but you'll probably use the proctoral as the proctoring, and we will take it during lab time on Wednesday. It will cover chapters 1, 2, 3, 4, and 10. Remember, chapter 1 pretty much didn't have anything in it, so there's really nothing from chapter 1. So really, it's 2, 3, 4, and 10. As I mentioned before, I don't even know if we really talked too much about chapter 1 or anything like that and stuff like that. Okay. All right, so that's the game plan. Any questions on that and sort of what's going on in terms of this week, next week? So again, there will be nothing due today in terms of the lab, because again, I'm going to save the lab until next week, and again, that should hopefully give us a chance to get a little bit of progress going into the next chapter, and maybe get to that second part of it with the electron configuration, and then it has some periodic trends, but then it has some stuff about the periodic table that we talked about today. So it's kind of a weird experiment. It covers multiple chapters, so we'll try to fit it in where it's probably most appropriate. All right, any questions on any of that before we get going?
So as it relates to the exam, there's very few calculations that we've done basically through these chapters. So is it going to be multiple choice questioning like the clicker questions?
Yeah, it will probably be similar questions to what we went over in class and examples and stuff like that. So there's definitely obviously going to be something, I would assume, calculation. Most of it will probably be calculation based. Some of it will be obviously non-calculation based, but we did do some calculations, obviously, like conversions, density, those type of things, sig figs. But towards obviously when we got to sort of the chapter here that we're in, where we're talking a lot more about the atom and stuff like that, there's going to be probably some non-calculation type questions involving that stuff. But even in this chapter, there's things like identifying the numbers of protons, electrons, neutrons, and stuff like that. So usually the exams are mostly, I would say, problem based. But again, since some of this stuff is obviously not really problem type based, There's going to be some, I would imagine, I don't want to say short answer questions, I guess something like that, less calculations. Other questions? Okay, so then let us continue on with chapter 4 here. And like I said, afterwards, we will get into chapter 11 and we'll wrap it up at some point today for the week. And that will hopefully at least set us up maybe a little bit better for next week. And maybe we'll get that experiment in there some point. All right, let us get started then. All right, so we sort of left off here on this slide talking about ionic compounds. And again, a reminder that ionic compounds is always pretty much made up of a metal and a non-metal coming together. And when that metal and non-metal come together, the result of that is an ionic compound being formed. And also the idea here is that's actually when these guys do gain charges. So these guys actually do gain charges when they actually come together. So as we were talking about earlier, if we have a metal by itself or a non-metal by itself, just from the periodic table, if you just take that thing by itself, A, it has no charge, and B, it will only really gain a charge when they come together. And it's only really when a metal and a non-metal come together that they actually do gain those charges, the positive charge and the negative charge. But one way you could always easily recognize something as being an ionic compound is just by identifying, oh, that's a metal, that's a non-metal. I definitely know that's an ionic compound. And you could definitely identify it by that. You don't even have to worry about anything else. It's always going to be probably 100% safe bet that goes, that's an ionic compound. That's those guys. They're not going to be sharing electrons. They have a transfer of electrons. And again, what holds that unit together is that positive negative attraction, which is what is referred to as electrostatic attraction, and that bonding that's there. And that attraction is a extremely strong attraction. When you have something that's positive, something that's negative, there's a very strong attraction between them. It actually increases with the charge. So something with a +3 charge and a -3 charge, they are much strongly attracted to each other than say if you had a +1, -1 sort of attraction. So as actually the charge increases, so does the attraction between those positive and negative guys. So when we do have an ionic compound, when we do dissolve it, we'll break apart, as I mentioned at the end there, into ions. And those ions are very helpful in conducting heat and electricity and conducting really electricity. And when they do that, they are sometimes what are referred to as electrolytes. It's something that can conduct electricity really well. And that's why we don't, blow dry our hair in the shower, because there's a lot of ions in there. Otherwise, you get electrocuted and all that good stuff, because it will conduct electricity really well. Oddly, water by itself, just H2O, nothing in it, pure water. It's a very bad conductor of heat and electricity. And as I just mentioned, the water coming out of your pipes is not pure water. So do not blow dry your hair in the shower or anything like that, because you will get electrocuted. They actually do put ions in water to clean it. And so it has a lot of ions in it, and it conducts electricity really well. Now, when we do have an ionic compound together, whenever we take that positive guy and that negative guy and we put them together, we always want the overall charge in the formula to be 0. So we always want to balance the positive guy and the negative guy. And when we get the bonding, we'll really learn why that is. But the reason really is that in order for them to come together properly and everybody to have sort of the right amount of electrons in that arrangement, they need to come together in the simplest way that you could get it to equal 0. And this is just simple as that, positive, negative guy. When you put them together, they need to balance each other out. So when we write formulas for ionic compounds, so for example, if we take a magnesium, which as we saw is group number 2, forms a +2 charge, and we put it together with a chloride ion, which is group 7, has a -1 charge. The very simple way to think about this is I got +2 and -1. So to balance it out, I need not one of the chlorides, but I need 2 of them. -1 and -1 gives you a -2. The -2 and the +2 balance each other out. So when I write the formula, as we can see below, the correct formula is MgCl2. Again, remember the little number means how many we have of the guy next to it. And what this implies is magnesium, that we have one of those and it has a +2 charge. This implies we have two of the Cl minuses, each at -1. So -1 gives you -2 and your +2. Now, sometimes people go, I could just do the crossover move, like move these guys down. And it does work most of the time, like 90-ish% of the time, 92% of the time. So if you're good on the kind of crossover move, you could do it just blindly and cross them over. Won't work 100% of the time. So it's good to think about it in terms of balancing out the charge. Just like if I had a sodium, which is group 1, and nitrogen, which will form a -3 charge. When I put these together, -3 on the right, +1 on the left, tells me I need not one of these guys, but I actually need 3 of these guys, which gives me a grand total of +3 and -3. So when we put it together, the formula is Na3N would be the right way to put that together. Again, implies that I have 3 sodiums at +1 each, +1, +2, and +3 total. I have 1 nitrogen at -3, and that means that it's -3, +3, everything balances out. Again, this is a situation where if you do the crossover thing, it will work. But again, you could also go the opposite way and cross back. Again, it works about 90 some odd % of the time, not 100% of the time. So good just to think about it in terms of balancing out the charges and stuff like that. So although when we write the formula like we did for this guy, it does not have a charge and it should never have a charge. If you're asked to write the formula for just the cation by itself, it should have a charge. So this, the cation, would have a charge. It would look like this. And if we write the formula for just the anion, it would look like this. So if you're asked to write the formula for the anion, it should be Cl minus. And very often people do this move and write like Cl2 minus because there's a 2 there, and you shouldn't do that. So if you're asked just to write the formula for just the ion by itself, what you want to do is take just the individual ion out, one of those ions all by itself, and what the charge is on it individually if you're asked to write the formula for the ion. Again, you don't want to kind of incorporate that subscript there. Question on that. So ionic compounds, important thing, all the positive charge, all the negative charge, they need to come together to equal 0. And the way you do that, again, is the simplest way you could get it to 0, to equal 0. Any questions on that? All right. So why don't you take a second here and write the correct formulas when we put these guys together and see what you come up with. Okay, so let's take a look here. So again, the idea is we want to put these guys together to equal 0. So we have aluminum with +3. We have chloride with -1. So when we put it together, we do need more of the chloride. So you can just even draw it out if you want. We need 3 total of them. So when we put them together, we should get AlCl3, 1 aluminum at +3. 3 chlorides at -1 each gives us -3 and +3. This would be the correct formula for when we put it together. Sn here is tin, and it has a +2 charge, and S2 minus is sulfide, and we got -2 and +2, which means when we put this together, we just simply need one of each of those to get the proper arrangement. So we have one tin at +2, one sulfur at -2, +2 minus 2 gives us 0. And lastly here, if we put these together, the common number between 2 and 3 is 6. So to get copper to 6, we actually need like 3 of them. And to get nitrogen to 6, we need 2 of them. Right, it gives us 6 and +6. And that would give us Cu3 and 2 again. This is sort of a crossover move, but it will get you the right answer here. Question on any of those formulas? So since we talked a little bit about naming these ions individually, this would be the aluminum ion. This would go from chlorine to chloride. So when we would name something like this, we would actually just put them together. This would be aluminum chloride. This is tin. If you look at the periodic table, tin is located not in the transition metal, but just underneath the staircase here. And if you remember, we were talking about these guys in this area where tin is, lead is, bismuth. They have variable charges. So if we were to name this cation, this would be tin Roman numeral 2. The 2 is for the charge, and we would need it here because something like tin could be like +2. Something like tin could be +4 as well. This is our nonmetal, which goes from sulfur and has the IDE at the end of it, sulfide, IDE ion. And we put those names together. That's how we get to this guy. This would be tin Roman numeral 2, and it becomes sulfide, IDE. And again, the reason we need the Roman numeral is tin has the ability to make multiple types of charges. So literally we need to tell people we're talking about the tin with a +2 charge here. Same thing with copper. If you look at copper, copper is smack dab in that transition metal region, which means it also can have multiple charges, which means if we were to name the cation by itself, this would be copper Roman numeral 2, again, the 2 for the charge. And nitrogen begets the IDE at the end of it and goes from nitrogen to nitride, IDE. This would then be known as copper Roman numeral 2 nitride. Again, we did not need a Roman numeral here on this guy because he has a fixed charge. So he's group number 3. He's always going to be +3 no matter what the situation is. So you don't need the Roman numeral on that. Any questions on that preview of naming, which is in a later chapter as well? Any questions on that there? Okay. So again, putting together, you want to make sure that you get it equal to 0. And again, it is the simplest way to get it to 0 is the important part there. So take a second here. Which one is the correct formula for when we put calcium together with oxygen? Okay, so to help you decide on this, you can use the periodic table to help you. And if you look at where calcium is, it's right here in group number 2. So everybody in group 2 has a +2 charge, which means we know the cation here is going to be calcium with a +2 charge. Oxygen is over here in group 6 on the periodic table. Everybody in group 6 has a -2 charge, and that means that our anion here would be -2, which means to put them together, we just need one of each of those, and we end up with this here, and that would be D, it looks like. Now, if we were to name this, so calcium, because it has a fixed charge, just going to be called the calcium ion. Oxygen, which is our nonmetal, gets the IDE at the end of it, so oxygen becomes oxide. And again, this guy, when we put it together, would then just be called calcium oxide in this case. Again, no need for a Roman numeral here because calcium has a fixed charge, so it's always going to be +2 no matter the situation. So again, the Roman numeral just used to indicate the charge of something that has a variable type of charge. Question on that one? And here's aluminum. When aluminum metal is dropped into liquid bromine, the ionic compound is aluminum bromide. What is the correct form for aluminum bromide, the formula here? Okay, so same idea here. We want to use the periodic table to help us. If we look on the periodic table, we're going to find aluminum there in group number 3. And that means that aluminum will always form a +3 charge. It's got a fixed charge. Bromine is in group 7. And everybody in group 7 will form a -1 charge. So again, when we put this together, we need not one of these guys, but basically we need 3 of them to get to our -3 to balance it out, which means aluminum bromide would look something like this, which looks like it is C. And the name here, which is aluminum bromide, the idea is aluminum, again, a fixed charge, so don't have to worry about any Roman numerals. And the bromine becomes IDE at the end of it, which is bromide. So again, there is a difference when you say something like, I have bromine versus I have bromide. Bromide is the ion version. Bromine would be the element version, which in this case would be Br2. So although it may seem like they're the same thing, there is, again, actually a difference in terms of what it means when you sort of give a name, bromine versus bromide. So there is a slight difference there of what it actually means. Question on that one there. And to finish this out, a member of the alkaline earth metals whose most stable ion contains 36 electrons forms a compound with bromine. What is the correct formula? So we do want to sort of identify it based on alkaline earth metals. So calcium is an alkaline earth metal, which would be the first guy. It's always the positive guy first. It's so in an ionic compound, it is always metal first, followed by non-metal when you look at a formula or a name. So calcium here is our metal, and that is alkaline earth metals. The next one would be Kr. Krypton is a noble gas. which would mean probably not the right answer. Rb, which rubidium, is group 1, which is an alkali metal. So probably not the right answer either. Strontium is also an alkaline earth metal. So we do have a choice between these two guys. So it does say that the most stable ion confers 36 electrons. So if we look at calcium on the periodic table, that is number 20. We look at strontium, that is number 38. When calcium makes a +2 charge, like it will end up with 18 electrons. When strontium makes its +2 charge, it will end up with the magic number of 36 electrons. So although these both are alkaline earth metals, the one that has 36 electrons would be our guy here at the end. So it should be strontium bromide, and the name of that would be strontium bromide. Again, strontium has a fixed charge of 2, so no Roman numeral needed. Question on ionic compounds, how to put them together correctly, and those type of things. That should wrap up chapter 4 and what's going to be on the exam, which again will be 1 week from today, Wednesday, during lab, and it will cover everything from chapter 4. Now, we did do some naming here in chapter 4. You're not going to have to worry about naming for this exam. We're going to officially talk about naming in a later chapter. So for this exam, you really just need to focus on, in terms of ionic compounds, putting them together correctly. So you do need to know the charges of those ions in groups 1, 2, 3, 5, 6, and 7, and be able to kind of put them together. You won't have to worry about the naming aspect of it, even though we sort of did a little bit of it here. Any questions on that? Also, I don't know if you saw, but up online in our Canvas site, I think right above this week, I did put up some review stuff for exam 1. So there's kind of a review topics sheet of all the topics from exam 1, stuff that you need to know. There's also some worksheets / more information on certain topics like sig fig, specific heat, those type of things. So you might want to check it out as well. Any questions on that? Okay, we are going to roll then into chapter 11 just to kind of get us on track for a little bit here until everybody's head hits the desk and can't take it anymore, and then we will call it a day at some point. I include myself in that conversation as well. So. Okay, so we're off to chapter 11, and we're going to really talk a lot more about electrons in this chapter, including electron configuration, where electrons are sort of in the atom, and some other stuff here. See that there, maybe. All right, here. Just close that out real quick. Try it one more time here. Okay. Does it all look okay on your side? Everything's kind of the right size, or is it like small? Looks okay.
Can you full screen it or no?
Okay, yeah, let me try again here. So let's see here. Is that better or worse?
Yeah, that's good. It's perfect.
Thanks for letting me know. Sometimes on my side it just looks the same. So I was like, I'm not really sure. All right, perfect. Okay, so in this chapter, we're going to talk about, like I said, pretty much electrons, where they are in the atom, what happens to electrons as they sort of transition from one energy level to the next, and what happens in terms of the energy that happens when they do those transitions. And then towards the end, we'll talk about some periodic trends and that type of stuff. All right, so we talked a little bit about Bohr and his sort of model of the atom. And again, the nuclear atom, not really Bohr, but we talked about the nuclear atom. Just rearranging some stuff here. Perfect. The atom, as we talked about in the previous chapter, again, has that really small, dense nucleus That's where we have our protons and our neutrons found. And remember that our protons have a positive 1 charge and our neutrons have no charge, but it is most of the mass of the atom is made up of that nucleus. And that's because we have electrons on the outside really kind of flying around in that empty space. And as we sort of alluded to in the previous chapter, they really don't fly around in pretty little orbits or anything like that. They do move around really randomly throughout the atom within that empty space. And some experiments really led us to understand that at no given point can we know exactly where a particle like an electron is and how it's traveling at the same time. So one important sort of thing that we'll see in this chapter is that idea that as we sort of know more about where we think an electron is, we know less about how it's actually there or traveling and stuff like that. And that's what is sometimes referred to as the Heisenberg uncertainty principle that we'll talk about a little bit later on in this chapter. So what's happening with these electrons? Obviously, the positive nuclear charge is present as those electrons are moving away. They are kind of moving around, but there is some attraction that has to happen, right, between our negatively charged electrons and our positively charged nucleus. So although they are away from the nucleus, they are traveling in these sort of random patterns, certain electrons will feel a sort of attraction to the nucleus as they're moving around. Other ones will feel an attraction as well, but not as much of an attraction as they are sort of further away from the nucleus. And so we're going to kind of think about how they can move and how they move about the nucleus. And this brings us to an idea of what is referred to sometimes as the sort of quantum mechanical model of the atom. And there was sort of this early idea of electrons moving around in these pretty little circles, and that's what's sometimes referred to as the Bohr model of the atom, that they move in what are referred to as orbits. And these orbits basically mean that these electrons we know for sure are in this orbit or that orbit, and it's traveling around these pretty circles. And this was sort of later maybe disproven a little bit through what is known as a quantum mechanical sort of model, where the best that we could do is go, I'm not really sure how an electron is moving. The best I could say is that there is a high probability of finding an electron in a particular location in an atom. And this is how we sort of move away from a couple of terms that we'll probably see in this chapter, where we think about electrons moving around these orbits, kind of like a planetary model, to what is referred to as orbitals, as to where they are sort of housed in an atom. And as we will see in this chapter, orbitals are more theoretical probability type maps of where we can anticipate maybe finding an electron in an atom. So a lot of this does involve waves. And when we talk about waves, there's certain parts of waves like the wavelength, the frequency, and the speed. And when we talk about waves, you know, a wave looks something like this. And basically, there's some different parts of the wave, as we will see, from sort of crest to crest is the wavelength, which is abbreviated with the lambda symbol. You go trough to trough as well. There's sometimes the amplitude, which is sort of the midline of a wave. We also have the frequency, which is basically how many waves sort of pass a particular point in a given second. And we have also the speed of a wave. And waves really important, and ultimately where waves sort of tie into what we're talking about in terms of electrons is sort of a preview is if we have sort of an energy level, and we have an electron on a lower energy level, and it gets itself up to a higher energy level, it requires a certain amount of energy to do that. And what usually will happen is that electron will then find itself wanting to go back down in terms of energy. And since there's that conservation of energy that we talked about in an earlier chapter, the idea here is in order to allow that electron to go up in energy, it has to gain a certain amount of energy. And in order for that electron to come back down in energy, it has to give off a certain amount of energy. And oftentimes when that electron, for example, comes back down in energy, it gives off that energy really in the form of a wave that has a specific wavelength. And this is sometimes what is referred to as a photon of light. And so really what waves do a lot of times is they're able to transmit energy through space, and energy is kind of moved around through space in the form of waves. And as we'll talk about a little bit in this chapter, depending on the wavelength that's there, it may correspond to something where we see light, for example, like when we shoot off fireworks, right? When we shoot off fireworks, they explode. When they explode, all those elements, they gain a tremendous amount of energy really quick. And what happens really in like fireworks is when those elements gain all that energy, all their electrons decide we're going to a higher energy level. But much like us, as we'll talk about in this chapter, we like to be in a lower state of energy. So those electrons want to come back down in terms of energy. And as they are coming back down, they give off energy in the form of a wave that corresponds to the visible part of the spectrum where we see colors. And we look up at the sky and go, pretty red, pretty purple, pretty something color. And we're able to kind of see color as these electrons are transitioning down. A simpler sort of example of that maybe you've done if you've cooked pasta before on the stove and maybe your water over boils and the water hits the fire. When the water hits the fire, it sometimes turns like a yellow or orange color really quick. And that's because inside your water, you probably threw some salt, so you got some sodium in there. And when that sodium ion hits the flame, it gains all that energy. Its electrons go up in energy. They're coming back down. And what you're visually seeing is the energy being given off as those electrons come back down, and it appears in the visible part of the spectrum. So to us, it appears that, hey, look, the flame just turned yellow or orange or got bright for a second. And that's a lot of what we're going to be talking about is this relationship between energy and waves and as electrons basically transition. So let's talk a little bit more about sort of waves and sort of what happens with them. So as I mentioned earlier, the wavelength, which is sometimes abbreviated with the lambda symbol, is the distance between two peaks or troughs in a wave. Usually the wavelength is given in units of meters, so usually we give it in terms of units of meters. The frequency is the number of waves that basically pass a particular point in a second, and it has units of reciprocal seconds typically, and that's what this is. This is reciprocal seconds here. Or it has units of hertz. So a hertz and a reciprocal second are the same thing. They are a one-to-one relationship. So 1 hertz is a 1 reciprocal second. So if somebody says you have a frequency of 4 times 10 to the 14 reciprocal seconds, or you have a frequency of 4 times 10 to the 14 hertz, it's the same thing. The units are basically a one-to-one relationship. You just change the units, the number stays the same. Hertz, you may also be familiar with if you tune your radio to a certain dial, right? You grab a little 101 megahertz, which is basically the radio station, right? Or 95.5. When you dial it into something like that, that is megahertz, and that is the frequency of the radio waves. And radio that comes through your speakers, also waves coming through, and they're what are known as radio waves. They have a longer wavelength, not as much energy, and that's, you know, that relationship there. C is the speed of light, and that's the official number there, but I think most people round that to 3 times 10 to the 8 meters per second. I personally use this number. If you want to use the one with all the 0.9979, you can, although it usually will probably round out at the end anyways. So 3 times 10 to the 8 meters per second is the speed of light, and that's a constant. So you always have that number. And you could use these relationships to calculate things like wavelength or frequency using this formula here. So C is the speed of light, which is our 3 times 10 to the 8 meters per second. This is our wavelength in meters. This is not a V, it's actually a nu. That's what the name of it is, although most people call it V. But it is the frequency. And again, that's in reciprocal seconds. So if you just look at the units here, C is equal to meters times 1 over seconds, which gives you meters per second for C. And that's the unit. So we could use this to solve for something like the wavelength. We could also use this formula to solve for something like the frequency of a wave by plugging those guys in and putting it in the correct units. If we rearrange this, the wavelength would equal C divided by the frequency. And if you wanted to solve for the frequency would be C divided by the wavelength. Again, C is a constant, that 3 times 10 to the 8 meters per second, and you always have that number. The relationship here is the speed of light is inversely related to each other, as you can see there. So as one goes up, one goes down, sort of that relationship there, inversely related to each other between wavelength and frequency. Now, when we talk about waves and sort of energy, as I mentioned before, there is a relationship between the wavelength and energy and frequency. If we have a longer wavelength, we have a lower frequency, and that usually results in lower energy. And that's opposite if you have a shorter wavelength. Shorter wavelength usually happens very quick and has a higher frequency and has a higher energy. So there is a direct relationship between the wavelength of light and the energy and the frequency. So here's actually 3 waves that represent 3 different colors. And this is part of the visible part of the spectrum where we see colors like red, green, and blue. This is like where that famous Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, and violet. That is the visible part of the spectrum where we actually do see color. So what that means is, much like fireworks, much like if you ever done a flame test before, when you see the electrons go down in energy and it gives off a wave of energy of light and it falls in the spectrum somewhere, we will see the appropriate color based on the wavelength, you know, be it 700 nanometers, 500 nanometers of light, something like that. So what we see here, if we compare these 3 colors, just by looking at the waves, we see that the wavelength for red is longer than the wavelength for green, than for blue. So we can make a pretty safe assumption that even in terms of color, there is a difference in terms of energy. Red would be the lowest in energy because it has a longer wavelength, a lower frequency, and would have lower energy. Out of these 3, blue would be the highest in energy because it has a shorter wavelength, a higher frequency, and results in a higher energy level. And we can even make sort of predictions, and sort of how this ties to what we're going to talk about in this chapter is, let's say we had an electron that was like on the first energy level, and we have one second energy level, say third energy level, and so forth. If my electron went from the third energy level all the way down to the first energy level, that would require more energy than, say, an electron that's on the second energy level that went down to the first energy level. And in terms of, say, the light, for example, if we had to choose, say, these were the 3 colors, we would probably predict that because this guy up here went the furthest in terms of energy, this would be more energy, and it probably would give off something closer to the blue light, maybe the green light. This guy only traveled 1 sort of energy level, which is less energy, which means if it was sort of a color that we would see, perhaps we would see more of a red color. Obviously, it involves the correct transitions there, but that's sort of the idea here. So you could almost kind of predict what colors you may see depending on how much energy levels those electrons need to transition down. And there's actually calculations where you could calculate the energy associated with that. So why don't you take a second here and give it a try. What is the frequency in hertz for light that has a wavelength of 7.8 times 10 to the 2 nanometers? And just a reminder, in case you forgot, nano is 10 to the minus 9. So see what you come up with here. Okay, so let's take a look here. So we want to kind of use that equation that we had before. C is equal to the wavelength times the frequency. So we're looking for the frequency. So to rearrange that, frequency would be C divided by the wavelength. Again, just dividing this to the other side. We do have a few unit type problems. C again is 3 times 10 to the 8 meters per second. My wavelength here is actually in nanometers. So I am going to have some trouble here if I don't do a conversion. So I'm going to convert the nanometers into meters first. So when we say this guy up here, what that means again is in 1 nanometer, there is 10 to the minus 9 meters. So remember, that is the way to use that properly, not reversed of that. So what we would want to do is take 7.8 times 10 to the 2 nanometers, using that as a conversion factor, 1 nanometer on the bottom, 10 to the minus 9 meters up on top. They cancel. You do want to make sure that you use your exponent button here when you do that. So remember 7.8 exponent button 2 times, that's basically 1 times 10 to the minus 9 with your exponent button. And that will give you 7.8 times 10 to the minus 7 meters. And now we have it in meters. Our speed of light's in meters. So we can go into this equation here. So we will have V is equal to 3 times 10 to the 8 meters per second divided by 7.8 times 10 to the minus 7 meters. Meters are going to cancel. And again, exponent button, so 3 exponent button 8 divided by 7.8 exponent button minus 7. We will go with a frequency of 3.85 times 10 to the 14. In terms of units, this is the only one left, and it is actually 1 over seconds that's left. Or if you want reciprocal seconds, or if you want, because that's all the same, it is a hertz. So that is how many hertz there are, because it's a one-to-one relationship, and it would be that many hertz. Question on that calculation. So again, you want to make sure exponent button, units correct and everything. Any questions on that? So just a relationship to, just to kind of tie this equation here that we use together with another one that you'll see in 1A for sure. We won't probably do too much of it in here, but we were talking about sort of the energy and stuff. where's that equation here? And we'll go here. So another sort of important equation in terms of energy that we sometimes come across here is one that's equal to E times H times the frequency. E is energy. H is what is known as Planck's constant. And that has a constant of 6.63 times 10 to the minus 34 joules times seconds. So that is a constant value. And our guy here is our frequency. So if you know the frequency like we just calculated, you could actually put it into here and calculate the energy associated with that wave. The nice thing about this equation and actually this part right here is if you take E is equal to H times the frequency, and since the frequency equals C over the wavelength, you could get the energy is equal to HC over the wavelength, which is another common version of this equation for energy that you see. And the nice thing about that is if you just simply know the wavelength, you could calculate the energy because both of these are constants as well. So just kind of point that out to you. Again, that is an equation that you see a lot when you start talking about things like that. And that is sort of the relationship there, that H is a Planck's constant, C is the speed of light, and the wavelength. So what that gives you is really an opportunity is if you know the frequency of the wave, if you know the wavelength of it, you can actually calculate the energy associated with it by using that equation right there. Question on that there.
Could you just, what is the number by the 10 on Planck's constant on the bottom? Is that 34?
It is. It's to the minus 34.
Okay.
And the units are joules, which is a unit of energy, times seconds, which is obviously time.
Okay, thank you.
Other questions on that? Okay. So as I was mentioning, a lot of what we're really going to be talking about here is the idea of these electrons transitioning from different energy levels. And again, if they need to go from a lower energy level to a higher energy level, it's endothermic. So energy needs to be put in the form of energy or a wave. And if they're going from a higher energy level, those electrons to a lower energy level, they need to give off a certain amount of energy in the form of a wave. And again, as I mentioned, depending on the wavelength of light that's coming off, it may correspond to different parts of what is known as the electromagnetic spectrum, which is what we're looking at here on the screen. The electromagnetic spectrum is broken off into different parts. So on the far right here, we have radio waves, like when we were listening to the radio in the car. Then we have some microwaves. We have infrared, IR. This again is the visible part of the spectrum. That is where we see color. And that is what we were just talking about with our Roy G. Biv, right? Roy G. kind of Biv going on this way, right? So our red, orange, yellow, green, blue, indigo, violet. And then past that, we have ultraviolet, which is UV in that wavelength. We have X-rays, and we have gamma rays that we talked about, which is just really pure energy, right? Pure radioactive energy, very similar to neutrons, have no charge, very high in energy. If we look at the wavelength, which is on top, over here, we have 10 to the 4th meters. Over here, we have 10 to the minus 12. This is a much shorter wavelength on this side than on this side. This is a longer wavelength. And as we just talked about in terms of energy, what that means is on this side is much higher in energy. And on this side, it is lower in energy. And that makes sense if you think about it. Going kind of right to left here, radio waves have a certain amount of energy. When we get to microwaves, there's a little bit more energy happening. You can spin your water molecules really fast in your pizza, so it cooks very quick. If you go to infrared, that's typically where we feel heat. Visible is where we see light. UV is much higher in energy as well. That's why we put sunblock on when we go outside, so we don't get burnt or anything like that, right? We need to kind of block those really strong ultraviolet light that has a lot of energy, cause a lot of damage. X-rays, that's why when you take X-rays, right, they put a lead vest on you. They leave the room when they take the X-ray and all that kind of stuff. Very high in energy. And like I said, gamma rays are basically just pure energy, super high in energy, as high as you could kind of get. So as we go from right to left, that is what's happening in terms of energy is getting higher. Now, when we talk about these electrons and as they transition and they give off a certain amount of energy in the form of a wave, that wavelength may fall in this visible part of the spectrum. And again, we would see color. That wavelength may also fall like in the infrared part of the spectrum where we wouldn't see color, or the ultraviolet or any of those type of guys, but we may feel something else. We may feel heat or something like that in the infrared part of the spectrum. So not all transitions as electrons are transitioning from one energy level to the next will result in actually colors that you can see. They don't always end up in sort of the visible part of the spectrum. They can end up in other parts of the spectrum, which obviously we would see or feel different effects, if you will. Obviously, the radio wave's pretty safe in terms of energy, low in energy. So as we're driving around, right, that's how basically through a certain frequency of the wave, right, it gets to our antenna that can receive it, and we can listen to the radio and stuff like that. And again, obviously, microwaves, a little bit more energy, you know, so as you go from right to left. So you do need to know this electromagnetic spectrum. You do need to know the different parts of it, the radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma. You do not need to know it in terms of the actual number where they are, but you do need to know it in terms of putting it in order from, say, highest energy to lowest energy, longer wavelength to shorter wavelength, higher frequency to lower frequency. Also in terms of colors. So as we mentioned before, red is about 700 nanometers or so, and that is lower in energy than, say, a blue color or violet color or purple color, which would be higher in energy. So a red wave of light would be lower in energy than a purple. Yellow there would be lower in energy than, say, blue, and so forth. So you need to know these things in that sense, the order, and be able to put them in order. So if you're asked a question like, put these four things in order of highest energy to lowest, you would be able to do that. Questions on sort of what you need to know from this picture here. So the relationship between a wavelength and frequency of radiation. So again, wavelength and frequency. So that is our C is the wavelength times the frequency. So if we just rearrange and solve for frequency, frequency would be C over the wavelength, or as we saw before, wavelength would be C over frequency. Since this is essentially a constant, this is the relationship of the wavelength is inversely related to 1 over the frequency, basically. So correct answer here should be B in this particular case, again, because C is a constant. Question on that one? Which form of electromagnetic radiation has the shortest wavelength? So the shortest wavelength would result in the highest energy. And out of all these, we got our gamma rays would be the highest in energy, followed by our X-rays, and then a little infrared, then microwaves, and radio waves being the lowest. So this guy would be the highest in energy, would be gamma. He would be the lowest in energy, followed by that order that I just did there. Question on that? So the concept of photons, particle-like nature rather than wave-like nature. So the idea is as these waves are being given off, there's a lot of experiments that were done to basically show that waves could have particle-like functions and particles could have wave-like functions. And that's how we could tie something like electrons to wave sort of function, if you will. So a photon of infrared light has more energy than a photon of, so we're looking at IR, and our choices here is visible, ultraviolet, X-rays, or microwaves. So if you remember sort of the order, if we had to put it, microwaves would be this way. Then we also have visible here. We have UV, which is ultraviolet, and we have X-rays going this way. Again, this is going to be higher in energy. This is going to be lower in energy. So the question is, which one, a photon of infrared light has more energy than a microwave in this case? So it would be D, looks like the answer here. It has more energy than a microwave. It would have less energy than a visible UV or X-ray in that particular case. So these would be sort of the type of questions like this, or questions like put them in order that you need to know from that chart. Again, you don't need to know exactly where everybody breaks off. Any questions on that? Okay. All right, so does not want to go back. Come back. No. All right, so we'll talk about what it says. It does not want to go back apparently. But when we talk about sort of these electrons transitioning from one energy level to the next, and in terms of energy, energy is thought of being what is referred to as being quantized. So quantized energy, or what is sometimes referred to as packets of energy, like it said on the previous slide. And it is sort of given off in that equation that we saw, which is that E equals H times V. They're sort of given off in these packets of energy. And basically what that sort of means, if you want to think about it, is I sort of equate it to like stairs, and electrons sort of travel like we travel on stairs. And what that means is if I have an electron and it wants to go from one energy level to the next, it will gain enough energy to go all the way up, say, to this energy level. Okay. Or if it just wanted to go to the next energy level, it would just gain enough energy to get itself up to the next energy level. An electron will never find itself like halfway between energy levels and go, I don't think I could get there. I don't have enough energy. So as electrons transition from one energy level to the next, is what is known as quantized energy, which means they either absorb enough energy to go from one energy level to the next, or as they come back down, they have to release enough energy to go from one energy level to the next. And the reason I kind of equate that to stairs is when we walk stairs, right? We usually, you know, nice stick figure here. We have enough energy to get to this step. We have enough energy to get to this step or this step. We never usually find ourselves like halfway between the steps and go, I think I'm good. I'm going to lay it up right there. Because if you do, you will lay it up right there probably, right? And fall over. Not so good. So when we do walk stairs, we definitely have enough energy to go from one step to the next. And if you've seen people walk stairs, which I imagine you have, I think I've seen people walk stairs. Some people can not only do one step at a time. It's been a while. I saw it on TV. I Googled it. But some people can do 2 steps at a time or 3 steps at a time, right? You know, they can kind of do multiple steps at a time. They have enough energy to go from one step to like the 3rd step or one step to the 4th step. Maybe not more than that, I don't think. And electrons sort of travel that way. Some electrons have enough energy or gain enough energy to go from one step to then just the next step or energy level. Some gain enough energy to go from the 1st step all the way up to the 3rd step and so forth. So when we talk about energy sort of being absorbed or given off by electrons, when we see these electrons transition these different energy levels, they are what are referred to as quantized energy or packets of energy, which means they always will gain or lose enough energy to go from one energy level to the next. And as we can see that, here's our relationship that we talked about earlier. We see our red guy less energy than our blue guy that has more energy. And if we had an electron that did a further transition in terms of energy, it perhaps would give off the blue light, as opposed to an electron that did a smaller transition in terms of energy, which may give off a red light in that particular example. Any questions on my wonderful stick figure drawings or anything like that, or the wonderful idea of stairs? Yes. All right. With that, words of wisdoms of walking stairs, I think we should wrap it up for this week and have a weekend and all that good stuff. So have a very good weekend. If you didn't type here, make sure you do so. A reminder that 1 week from today during lab, it is the exam. Probably mainly problem-based, but there will be some, written type questions. You will have to use proctorial and all that to take it. And like I said, on Monday, we will continue on with this chapter, and we'll get into hopefully the experiment that we postponed for today. All right. Any questions or anything? Okay. Have a nice weekend, everybody. I'll see you on Monday.